All right, we're on. Okay, hello everyone. Welcome to Kyverno office hour. Today we have Khaled on the line to demonstrate the framework of Kyverno performance. He'll showcase how performance testing is done in Kyverno against the latest version of Kyverno, as well as the enhancements since 1.10. So with that, let me hand off to Khaled. Stop sharing and take it away, Khaled.
Yeah. Hi everyone. So shooting, I don't think I can screen share now.
No?
Yeah, I can't.
Well, can you request that I can approve?
It's refusing to even press the button. Okay, sorry, I think this is something related to my UI. I will leave and re-enter the meeting in a second. Give me 1 second.
Okay.
All right. Can you see my screen now?
You sharing? Not yet.
Yeah.
Or is it just me?
I can see your screen.
Yeah. I can see your screen now.
Okay. Okay. Hello everyone. So as Shooting mentioned, today we will be talking about the general performance improvements we did in Kyverno. So a while ago at Nirmata, we received some reports that Kyverno or the Kyverno controller couldn't cope with high load. So seeing that we are the gatekeepers of every request that comes to the API server, we decided to investigate this and, of course, do some performance improvements. Today, I will be walking you through what we did exactly, starting from defining a baseline load that we can handle and improving on that. So, as usual, the first step in everything you want to improve is basically have some baseline tests that you want to pass. And for us, we have two kinds of tests that we are interested in. We want to scale, and that's why we want to focus on load testing. So we decided to dig on the internet on how we can do that. And we basically found a load testing framework called K6 that we are using right now, and we will continue using in the future. So K6 basically all it does is allows us to, in customizable way, to bombard the controller, our controller, the Kyverno controller, with a lot of requests and do some assertions on what we expect the result to be. And it will measure everything for us. It will measure the response time, which is the most important aspect for us here. So in essence, a K6 test basically looks like this. I've opened up one of the tests that we will be using today. This test basically all it does is just create a pod, an incompatible pod with a certain policy, and basically expect it not to pass. As you can see, the test is like really simple. These are some helper stuff. So is
Let me
I
mute them. Go ahead, Khaled.
Yeah, sorry. Okay. So okay. So these lines are basically some helper utilities. We don't need to focus on them. They are basically getting the base Kubernetes URL. Um, this is irrelevant to the test itself, but it's helpful to send the request to the API server. It's also coupled with this line, which basically gets the parameters to authorize to the API server. Again, irrelevant to our test. It's just some helper utilities. The core of the test is basically in these lines. So in the generate pod, in the generate pod function, we basically return a pod with a random name. So basically, we give it a random name, and then it generates a JSON for the pod. We would then proceed and send an HTTP request to the API Kubernetes API server to create the pod. So basically, you are asking it to, hey, can you create this pod? And we give it just a simple pod that's incompatible with the PSS policies. And we expect, of course, that if the PSS policies are applied on the cluster, that the request would fail. So here we are just asserting, hey, can we check that the response code is 400, that the request was rejected by the Kubernetes API server? Yeah, that's basically it. And then we pass this script to K6 and let the K6 do its thing. So now that we established that we have a test to test how Kyverno performs or how Kyverno performs, let's go back in time to version 1.11.0 of Kyverno. So yeah, okay. So here we are on version 1.11.0, which basically didn't have any performance optimizations. Let's run this test. First, let's create a cluster. So what I'm doing right now is I'm creating a kind cluster that has 3 nodes. And in this cluster, we will be applying or deploying Kyverno, the older version of Kyverno, the version at 1.11.0. And we will be running the K6 tests to see how it performs in this version. And we will take it from there. We will see the numbers, and then we will so that we can have a baseline numbers of that we can compare to in the future and know that we don't have any regressions. Sorry that I didn't do this earlier. It will take just a second. While it's doing that, I can talk about the next step. So the next step in our investigation was basically to figure out why the requests are taking so long. And this honestly falls into 2 categories. Okay, it's ready now. Let's just deploy Kyverno and wait for it to deploy. Okay, so in order to measure how we can improve this, we would basically need something called a profiler. So a profiler basically is a super program that runs as a parent, to our program. What it does is basically stops the Kyverno controller each few milliseconds and takes and it reads the registers. It reads the program counter registers from the CPU. It reads the stack of the CPU, the stack of the program in order to be of the Kyverno controller in order to be able to get what function is currently running. So say I have this program. It's a Go program, and this is a function. And in the main function, I call this function. I'm midway executing through this function. So I'm in this line. So what the profiler would do is stop the entire program, shut it for a few milliseconds. It would then read some registers. And in these registers, it would find that in the stack, I'm in this function. Okay, I'm calling this function. Of course, we are doing a debug build, so it knows the name of the function and where the function exactly is. So it's able to pinpoint exactly where in the code I am. Using that information, it would collect samples. So say I'm running the program for 10 seconds or 30 seconds, and each second I would stop the program 1,000 times. So that's 30,000 samples. For each sample, it would record the function I'm in. In the end, it would produce a report. This report basically tells us like where in the code did we spend most of our time. So if say this function was found in like 50% of the samples, that means that from the 30 seconds, 15 seconds were spent in this function. That would mean that this function is doing something like CPU intensive. Sometimes this makes sense that a function would take this much time. Sometimes it doesn't. And that's basically where things start to click. Hey, if this function doesn't require that much time, but yet it's still taking this much time, then something is wrong. We should improve it. Kyverno is now deployed. So what I'm going to do basically is do 2 things. Um, okay, I should have enabled profiling. I didn't enable it. I went ahead and stashed some changes that basically enables the profiler, but I would need to redeploy Kyverno for this to take effect. Meanwhile, let's just run the tests. Okay, so we have a script basically install the PSS policies and then run the test. As we said, this test expects the PSS policies to be applied in order for the pod to be rejected. And yeah, that's basically what the script does. It creates a new test namespace. It applies pod security policies and it runs the test using K6, and then it cleans up everything. It's done running. Let's have a look first. Let me redeploy Kyverno. Okay, let me redeploy Kyverno with the profiling changes. Meanwhile, we can look at the report. Okay. Okay. Yeah, it's this one. Okay. So K6 would produce a report that looks like this. First, it would verify that the that the assertions were right, that we asserted that every pod would be rejected, and indeed they were all rejected. So we passed 100% of the checks. And the most important aspect to us here is HTTP duration. As you can see, first I'm gonna talk about what parameters I passed to K6. So I passed to it like 25 and yeah, let's see, 25 and 250. What does these two parameters mean? So K6 has multiple executors, one of which is called the shared iterations executor. The shared iterations executor is basically creates like a number of concurrent requests that are always open. So say I have like 25 concurrent requests. This is basically what this means. That 25 means 25 concurrent requests that are running in parallel. So at any time during the test, there are 25 requests open to the API server. Um, and the second number is the number of iterations. So the number of iterations is evenly distributed amongst the open connections. So if like the first connection finished the request, it would then queue another one from the 250, and it would basically uh, -1 from the 250. So now we have only 249 iterations remaining. That's basically what these two numbers mean. Um, in the num in the duration here, as you can see, that it takes a humongous time to just run 250 iterations. To just create 250 pods, it would take each pod like half a second, which is insane if you think about it. And that's not even the worst about the worst of it. Like most of the pods took around 751 milliseconds. Again, more than half a second. Um, this is basically unacceptable for a gatekeeper, someone that always is there when a request is sent to the API server. And that's why it was essential to us to, you know, improve things performance-wise. So again, how do we do that? We would refer back to the profiler. I'm gonna run this test again, but this time with the profiler. I'm just gonna verify that the profiler is already running, and then we will run the tests. Okay, so yeah. So it's indeed running. That's good news for us. Okay. So as I said, I'm gonna run the profiler. The profiler would basically um, run our program, stop it every few milliseconds, takes a sample of the stack, and then it would figure out the running function, and we will see the report at the end. So I'm gonna run the report, and then I'm gonna run the test again. Okay. Um, Here we go. I am running the profiler, and I'm running the test. Yes, here. Okay. Now it's bombarding the Kyverno controller with pods, and this should affect the profiler results. It's gonna collect the profile samples for a bit. I think that's by default 30 seconds. We can control that using parameters, but yeah. 30 seconds will be enough for our case. And in the end, we can, yes, it's ready. Okay. Okay. I don't prefer this view of the profiler, so let's change the view. There are two that makes sense for us. One of which is like very popular. It's not specific to vprof, but it's very helpful. It's called the flame graph. So basically, the flame graph would have like some sort of bars. Each bar would represent a certain function, and the width of the bar would basically tell us how much, um, in how many samples did this function appear. So it's mostly a percentage. So if say like this is by eye, just takes like 25 or half a quarter the screen, then this was running for quarter of the time of the samples that were taken using the profiler. Another view that I really love for using vprof is basically no, not this one. Yeah, let's go for the top. This is the simplest view, and it's the most important one. It basically ranks function from top to bottom on which one did take the most time. And from a quick check, as you can see, we find that a lot of the time was spent using for encoding and decoding JSON. So as you can see here, this is basically for garbage collection and whatnot. We don't care about garbage collection. That's something related to the go runtime itself. It's out of our hands. Yes, we can configure it or can try to control it, but that's not mostly due to bad code from our side. As you can see, again, most of the time is spent in encoding and decoding JSON. Okay, so again, we did further investigations using the profiler to basically know which function in our code is causing this encoding or doing the encoding and decoding. Using the profiler, we were able to pinpoint that to the context. Okay. Okay. To the context functions in the engine. What is it? Yeah. So in the engine, we have some sort of context that basically does, it's sort of a context store with a time machine. So if like we have a resource, we would add this resource to the context. We would then later query it. To be able to see some use of this, we would just go to its unit test. It's very helpful in identifying what the context basically does, what its job is. So as you can see, we have a raw resource. It's just a pod with some labels, spec volumes, etc. Doesn't matter. Some user info, some user request info. We would then create a new context, a new engine context, add the resource, and then add the user info, and then add okay, and then later we would query these. Later we would then query these this context for some information. So, for instance, we did add the resource already, so we can just query for the request object API version, and then yeah, in the test we would expect it to be v1 because here it was v1. So this is basically what the context does. It's a simple thing. It's used for a lot more things, but we don't want to talk about that now. It's irrelevant. But as you can see, this is taking a lot of time for just a simple query. Like, hey, I'm storing some information and I want to query it. It's taking a lot of time. Again, we have a problem. How do we solve it? First, we start with some baseline tests so that we can test whether any improvement we do is any good. Is there any regressions in the future? And again, in order to do that, we would have to do some sort of test. So this is exactly what I did here. The standard Go library or Go in general, in the testing package, also I have some sort of benchmarking ability. So I've added a benchmark here using the testing package. Again, it's doing much of the same thing. It's having it's creating a raw resource, user info, user request info. It's creating the engine context, adding the resource, adding the user info and the service account, etc. And then in the end, it's just doing some queries. Again, this is simple enough, but it's taking a lot of time. And in order to to have proof of this, okay, I'm gonna interrupt the profiler. Let's run this benchmark, right? Okay, okay. Running it is simple. It's just go test hyphen bench. And if you wanna do some memory benchmarking, you can also pass hyphen bench memory. This is basically just selecting the test itself. Okay, so here we have the results. Here it's telling us how many nanoseconds it's taking per operation and how many allocations it's doing per operation. An operation basically a single um, is a single iteration of this for loop. So each iteration of this for loop is doing like 432 allocation, which is insane for just querying a single, um, just querying the API version. This is like a lot, and it's taking also a lot of time to query this operation. Let's store this somewhere, because all right, sorry. This is very important. Again, this is our baseline. This is gonna determine if we improved things or regressed over things when we do our optimizations. So yeah, let's have it stored some here until we can um, later test it after optimizations. Okay, so we have now profiled everything. We have our baseline tests. What do we do from here? One of the things we did is this was one of the areas where we improved the performance. So basically, again, we were storing everything in JSON, doing a marshalling to merge both the new changes and the new things we want to add to the context. It's taking a lot of time. So we decided to um, use in-memory maps using just Go maps. So everything is done in memory, everything is done efficiently using Go maps. Um, and yeah, that's basically the gist of the change itself. I don't want to delve into details. You can check the PR. I don't have the PR on me right now, but I don't know how we can send it to you guys later. Maybe we can put it in the YouTube description. But yeah, you can check the PR for the details of how we improved things in the engine context just using in-memory maps instead of JSON context. But I'm gonna jump ahead into the main branch where everything's fixed. All right, it's saying that the changes will be gone. I mostly don't care. It's also stashed, so sure. Discard everything. Do we have anything running? No, we don't. Okay. Let's switch to main. This is the branch that has um, the new code, the new performance optimized code. What I'm gonna do right now is, again, let's have the same test benchmark, accept both changes. And okay, we have the same benchmark, only this time it's benchmarking against the new code. The interface stays much the same. Again, I didn't change anything. This is the same test from the last time. I'm just creating a new context, adding the resource, adding the user info, and adding the service account. So let's run the benchmark and see and compare both of them, both of the results. Um, it's gonna finish any minute now, any second now. Yes. So here is the new result. Let's copy this, paste it underneath the old results, and let's compare both of them. So as you can see, we improved things by a lot, and I mean a lot, like really. Like for a simple query, we only do 13 allocations, which is sensible. It's sensible. Again, it's kind of a lot for a query, but again, it's more sensible than having 342 allocations per operation. And it's the same thing with the time taken. As you can see, we have like a mind-boggling 20 fold improvement over the time we can do query, uh, over the time where we can do the query. And yeah, so as you can see, with a simple change, just replacing the JSON context with an in-memory map, we did improve performance by a lot. This is not the single the only change we did regarding performance. We've had a lot of changes also. So again, using Profiler, we were able to identify that we use James bus a lot to query the JSON context. And for each request, we were creating the James bus interpreter from scratch. And this wasn't necessary because we could create it only once and reuse it across multiple calls. And that's another change we did. Again, improving performance by a lot. What else? Yeah, we also used JSONiter, which is basically okay. Okay, so JSONiter is a Go library that's much faster than the standard Go library, JSON library. This also helped us improve performance by a lot. And finally, something that has to do with stability, not performance. Basically, when doing the load testing tests, we would run 250 iterations and everything would be all right. But when we started to increase the number of iterations to 1000, the Kyverno controller would start to crash. It would repeatedly crash once, twice, and so on. So we couldn't really get stable results for or get benchmark numbers for this. So again, using the profiler, but this time not the CPU profiler, no, but the Go routines profiler, we were able to pinpoint that when we have like 1000 requests, each request would create around 4 events, and each event would create a Go routine. This is basically an implementation detail used by the client Go library to create events in the Kubernetes cluster. And each Go routine would again take some memory. And this basically would OOM kill our pod. Yeah, so it was not really stable. So what we did here is a simple change really. We just increased the QPS for client Go to be able to send a lot of requests and decrease the number of Go routines at any second. But we didn't want to increase the QPS of everything for all the requests, so we created a separate client for events. And yeah, things now are much more stable. We are able to handle easily 1000 requests iterations. So after all that talk, let's see where we are right now. If you remember, it took us like around half a second on average to create 250 pods for each pod, half a second for each pod. So now that we did our changes, we tested that they are indeed effective using benchmarks. We haven't regressed, we have moved forward. And we are now more stable than ever. Let's see. Okay. This is gonna take a while, so stick with me. I think we are mostly finished. I just want to show you the new numbers, guys. As you can see here, this is not entirely the new. Yeah, this is the old numbers, around half a second. Meanwhile, what can we talk about? Yeah, we are creating a blog post around the changes we made, which basically details or summarizes, not details, which basically summarizes what we said in this video. So please do check it out if you have time. And yeah, I think that's it. Of course, since we discovered the importance of performance testing, we are trying to incorporate it in our continuous integration cycle. So we already started some work on automating these tests. Okay, what was this sound? Okay. So we started working on the CI to incorporate these changes into our CI. We are also this is not only limited to validate. We have some other tests for mutate, and we are working on some tests for generate. Let's deploy. Okay. So yeah, you should expect Kyverno moving forward to only move forward this performance and not regress, hopefully. Um, yeah, that's basically a summary of our journey of how we improve performance at Kyverno and how we do testing in general. Okay. All that remains now is again to see the new um, times for the improved performance in the latest version. Uh, this will be released, I believe, around the end of this month in version 1.12. Um, so please, if you can do upgrade to this version, um, yeah, it will be a second, guys, and thank you for sticking with me. All right.
Think I lost for a second. I don't know if you heard my message. So I was asking if we can talk about the automation of the performance testing and what is our plan to, when that performance testing will be spun up upon releases and new changes.
Can you repeat that again, shooting?
Yes, so can we talk about the plan of the automation of the performance testing and how that will be done upon new releases?
All right. Okay. So I'm not sure if I think you said that yeah, you lost me some time ago, but I was just talking that again since we discovered the importance of performance testing in Kyverno, again because we are the gatekeepers of each request, we decided to incorporate this in our we decided to incorporate these changes in our CI or continuous integration. We're using GitHub Actions for CI, and basically we decided to run the load tests for each PR, for each new PR, introducing any kind of new feature or changing any implementation details. We started again with the baseline numbers, of course, not half a second for each request. No, for the new number, it's around 50 milliseconds, I believe. Sorry, let me resolve this conflict. Set, doesn't matter really, so that I can deploy. Okay, so again, well, we started with some baseline measurements, which is around 50 milliseconds for each request. The CI, again, would fail if this number is exceeded. Um, and yeah, so again, we should expect moving forward that requests with Kyverno should take around 50 milliseconds. We don't want to regress back from that. So yeah, does that answer the question, shooting?
Yeah, that's exactly what I was asking for. I think I missed that section. Thank you,
Yeah,
Khaled.
thank you, shooting. Okay. Meanwhile, while we wait for it to build, do we have another question? I can see that there are something in the chat. Okay. I think this is from an older office hours. Okay. Okay. Now that it's done, we can proceed with the load test finally. And it should be done any second. And again, if anybody has any questions, I'm here to answer them. So please post them on the chat, or you can just say them out loud right now. Okay. As you can see, it's definitely better than the last time. It's not around the 50 milliseconds I just mentioned, but it's definitely better than before. This is mostly because my machine, we are doing the CI tests on GitHub Actions and not on my machine. My machine is kind of slower than that, and that's why we have these numbers. But again, my point still stands. This is like a 5-fold improvement from half a second to 100 milliseconds, and even the 95 percentile numbers are better than 1 second. This is like almost a 4 fold improvement. Yeah, that's it. Thank you everyone for joining, and yeah, have a good one. If anybody has any questions, I'm here.
Thank you, Khaled. Those are exciting enhancements around performance, and it reduced to like less than 200 milliseconds for the average admission review duration. So all the fixes and enhancements, as Khaled mentioned, will be released in Kyverno 1.12 release. And yeah, we're excited to share that news with you guys, and hopefully we can get the Kyverno Viz, more stable and performed well than any of the previous versions.
Thank you, Khaled. Actually, it was very, very useful. Yeah, you did a great job. Thank you.
Thank you guys for joining.
All right, if no other questions, I guess that concludes the office hour. Thanks everyone for joining, and I'll see you in our next session. Take care. Bye.